Okay, today we talk about chapter 6 of aerodynamics, about three-dimensional compressible flow, an approach describing analytical and also numerical calculation of such flow based on potential equation. And this chapter we will discuss today is quite short. So I think today we will finish all theory devoted to incompressible aerodynamics, everything with information which I planned for study of this subject. And from next class, I will expect your questions about theory, your questions about work 1, 2, and 3. And each time when will be time of our class, we will do asynchronous. And I will recommend you video to watch to study more concepts of aerodynamics videos, which I already recorded in past. Please don't forget that you can ask questions in chat and also by voice. Today I can see discussion chat and I can read your questions. Then in next classes, since I will not teach synchronized classes, we will communicate by Messenger, by WhatsApp in the group, and also we can communicate in Aprender in the model. But just let me know if you submit some question there. I will prepare answer and we will meet in the time of our class. Also, another announcement I would like to make today is that end of semester will approach soon. We have 1 month, more or less, to finish all. And because of this, since we have many people in the class, I would like to start planning a schedule for oral test. I will share with you, as usual I do, I will share a table where each of you will select an appropriate time for each person. Then you will know exactly when your test happens, at which time you will know the link. No, link probably not. Probably I will call each one separately. And you can prepare for that date and make quite simple, for my opinion. To pass oral test, you need to know all theory I explain in aerodynamics and all theory that Anderson explained in the book. Okay, let's talk about chapter 6, three-dimensional incompressible flow. We remember a definition of potential equation that we had in chapter 3. Equation 340 is defining to us Laplace's equation in terms of potential function, where potential function is defined in equation 154 from chapter 2 as a function of velocity. Once we know potential function, we can obtain velocity components in Cartesian coordinate, polar or spherical coordinate, or in any other coordinate system. The boundary condition for calculation of Laplace's equation is presence of only tangential component of velocity and on the wall. And at the same time, equation 40a is describing this condition, saying that normal component of velocity on the wall should be equal to 0, or saying by words, we direction. It's simple. Velocity follows wall direction, so a scalar product of velocity vector and normal component, normal direction on the wall would be equal to 0. This boundary condition we need because Laplace's equation is differential equation must be set must be set boundary condition. Same as we had in bidimensional flow, in three-dimensional flow we have also source. It will be called three-dimensional source as an elementary flow for 3D space. Three-dimensional source equation is presented on equation 1, 6.1, where streamline function is given as a ratio between some constant strengths of source divided by r, distance in spherical coordinate system. These equations here are written in spherical coordinate system, as you can see on figure 1. So only radial component of velocity exists. It is equal to infinite value in origin of coordinates. Okay, in the source, once we have r equal to 0, that means that c is equal minus infinite at this point, and at long distance, potential function goes to be equal 0 everywhere. Analyzing this function, we see that if we would like to visualize potential function represented in equation 1, it will be seen as a spherical or spheres with the constant value of potential functions starting from origin of coordinates. Written in this spherical coordinate system, radial component of velocity is given, this function without number, and angular components of velocity, as you can see, are also shown. They are equal 0. No, just classical source. Just a classical source. Then we define our constant C, shown in previous slide. We use same concept as we had for bidimensional flow, that constant C is related to volume flow or mass flow rate for compressible flow. This one, mass flow, is equation which suits well for compressible flow because density is inside integral, so it's a parameter variable. And for volumetric flow or incompressible flow, instead of mass flow rate, we have just volume flow, lambda, where density is not present inside integral since it's a constant value. So our C constant strength of source would be equal to lambda volume flow divided by 4 pi from this equation for sphere. And substituting this constant in previous equations, we see radial component of velocity, Vr, which would be reverse proportional to distance in square, and potential function. And potential function, which would be reverse proportional to distance from origin of coordinates. Sorry, just a moment. Okay, we can continue. And as before, V theta and V phi are both equal 0. So source flow is describing to us distribution of velocity only in a radial direction from origin of coordinates in all direction, independent on two angles in spherical coordinate system. Since we give analytical solution of radial component of velocity or total velocity, which we have in this elementary flow, and we give function 7 of potential, we can define all flow properties at any arbitrary point. Three-dimensional doublet is defined similar to b-dimensional doublet as we had before. I would like to remind you that b-dimensional doublet is a combination of source and sink. For example, for 2D, we had source at point A and sink at point O. So flow which goes from point A is consumed by point O. And flow is going similar to how we describe that, magnetic lines. Yeah, magnetic field. Very similar to magnetic field. Flow going from one direction is consumed by point on the other part, on the other distance, on the other side of doublet. Distance between point A and O has a limit, is going to 0, but this is not the same point. So these point A and point O do not compensate each other. They work in pair, forming such a doublet. This doublet also is having very similar structure in three-dimensional flow. It's shown in equation 10, as you may see. Equation 8 is describing the potential function. Equation 9 is describing potential function in spherical coordinates. And equation 10 is describing velocity vector from this potential function. As you can see, velocity vector is dependent on r in spherical coordinate on theta. Okay, and is not dependent on phi. It's 0 component on phi. So it has just 2 components in radial and 1 angular direction. Function of 2 parameters, but in 3-dimensional case it will be three independent parameters, where a third parameter would be equal to 0. Visualization of 3-dimensional doublet is shown on figure 6.3. It's just a cross section of doublet. We can imagine this field in 3D space. It's like shape of an apple. A 3-dimensional doublet. Using concept of 3-dimensional doublet, we can describe flow over a sphere. This flow over a sphere would be a combination of 2 flows: uniform flow, which comes from infinite distance, V infinite, and the doublet, which we just discussed. Combining these 2 flows, or summating, let's say summating these 2 flows and finding components of velocity in radial and angular direction, we obtain equation 12, 13, and 14. We will see that one part is first part of these equations represents flow from infinite direction. It now is written in polar coordinates, not in polar, in spherical coordinates. And the second part, which I probably will mark with another color, with a blue color, represents doublet. Okay, this doublet. Red part is flow from infinite direction. Blue part is doublet. three-dimensional. Summating these two flows, we obtain flow over a sphere. As same as before, we have zero component of velocity on the second angle. It's not influenced neither by infinite flow nor by doublet flow. So we have velocity components. We analyze these distributions of velocity. As a result, we can see several equations. Equation 15 is showing to us conditions on the surface, or let's say streamline, which has zero value. I would like to remind you that a similar concept of zero value streamline to equation 15 we had in two-dimensional flow when we were looking for size of cylinder. Here for three-dimensional flow from equation 15 we obtain equation 16 as a radius of sphere. Streamline, which is describing a sphere where body shape is same as the shape of streamline, so streamline doesn't cross, any flow doesn't cross this streamline, same as physical body, so real flow cannot cross. In such concept, size of sphere can be determined by equation 16 from strength of doublet mu and value of infinite velocity v infinite. It works in the following way. If we would like to simulate sphere of known radius, we have to choose relation between strength of source and strength of doublet and infinite velocity in such way that ratio between them divided by 2 pi in power 1/3 would be giving these radius we need, or vice versa. We have radius and supply and 18 by known radius, which we would like to calculate in our task. So strength of doublet can be obtained if we know radius, or vice versa, radius can be obtained if we know the strength of doublet and velocity. Here equation 19 shows we have only angular component of velocity. According to boundary conditions, we remember that we cannot have flow crossing the sphere, so radial component of velocity does not exist, and only only angular component of velocity, which is tangential at any point on the wall of sphere. For example, here I show several tangential direction of velocity at this point. So this v theta exists. Vr would be equal to 0. A center of coordinates or origin of coordinates is at the center of the sphere. In such case, what we see from this picture, I think you can see something that is similar, not same, but similar to what we saw on the cylinder. First of all, analyzing pattern of streamlines, we see that streamlines are symmetric. In horizontal direction, and also streamlines are symmetric in vertical direction. Once we are looking on front and rear part from the sphere. So there is symmetry, horizontal and vertical symmetry of streamlines. It means that since horizontal symmetry exists, lift would be equal to 0, and since vertical symmetry exists, drag associated with pressure would be also equal to 0. So the concept which we examine today is allowing us to study approximate flow structure, but without any possibility to calculate even drag, not the lift. Lift would not be possible, right? Because it's symmetric. But even drag calculation is not possible because since we have symmetric distribution of streamlines, it means that we have symmetric distribution of velocities and symmetric distribution of pressure before and after sphere. It means that drag has no source. Or let's say differently, pressure forces are equal on the left and right side of sphere, so they are in equilibrium. It will be no difference. Since we defined analytically velocity, just a moment, here equation 19 showed us velocity on the surface of sphere, this analytical solution. We can obtain analytically pressure coefficient from velocity. Okay, we see that pressure coefficient can have at most be equal 1 when theta is equal 0. And also can be, I think it's -1, say or minus, probably -1. No, a bit less than -1. When, yeah, it will be, this part would be equal 1. So it's 1 minus 9/4 would be a bit more than, will be 125, minus 125, right? That gives us estimation of pressure coefficient, analytical estimation of pressure coefficient on the sphere, on the front part and on the top part of sphere. Here, figure 6 is showing to us comparison between pressure distribution of sphere and cylinder. This calculation, which we can analytically perform for b-dimensional. This is 2-dimensional case cylinder, and this is 3-dimensional case sphere. And we see that maximum is same for both. Maximum CP is equal 1, as we just saw on formula from previous slide. And minimal for sphere minus 125 analytical. And for cylinder, minimal is -3. Okay, a pressure coefficient has straight relation to velocity. It means that for sphere, velocity on the top of sphere here, let me go back to schematic. Here is CP equal 1. And here is CP equal -125. Small negative value of pressure coefficient. Analyzing together these two flows to distributions of pressure coefficient, we understand that velocity maximum would be smaller for sphere and higher for cylinder, because for cylinder we have smaller value of pressure coefficient. Smaller pressure, higher is the velocity, because we have conservation of energy. More energy is transformed to velocity. Okay, figure 7 showing to us an approach to calculate any arbitrary 3-dimensional body using source panel method. Is similar to panel method which we discussed for airfoil and 2-dimensional body. Here, in this approach, we distribute any arbitrary body in a number of panels. Can be this rectangular or quadrilateral panels, or could be triangular panels. And on each panel, we have constant values. of normal direction, we know size, and we have constant value of strength of source. Then we start to calculate a total potential function over these panels, and we see that potential function on each panel will be a sum of influences from all other panels. Such equation can be solved analytically, or let's say such equation system can be solved analytically, and we can find strengths of source on each panel with the boundary condition that normal component of velocity is equal to 0 on each panel, so flow is only tangential. And in such a way we can find solution. This method is implemented in several softwares nowadays. Is not so much useful, but in the previous years it was extremely important for development of many aerospace structures, for example, airplanes, space shuttle, other aerodynamic structures. You can see here picture from very old study design of transportation of space shuttle by Boeing 747. Such task of transportation is extremely important because it was produced in one place, launched in different place, and then landed on different place, and should be transported from one place to another. So such task could be solved with panel methods in some part, not in total, right? Not completely, because as you may see here, number of panels is not so big, so it does not describe perfectly all aspects of geometry of airplane and shuttle, but it allows to obtain some estimations about aerodynamic properties of this transportation, or possibility of this transportation. Of course, nowadays such tasks can be performed with very different methods and very different approach. For example, with CFD methods, it could be calculated much more precisely. I would like to remind you that this method you see is not CFD, is solution of potential equation, right, of just one equation, right? And it's many times more simple from computational point of view, from number of calculations and required time for simulation, and that time of design of such vehicles, it was the only method to evaluate aerodynamic properties numerically. So this was a huge advancement in computational methods. Nowadays, since we have powerful computer, this method is substituted by CFD, which is more accurate, much more accurate. Flow over a sphere, real case. Once we saw case of calculation by potential equation, here we can see flow over real sphere. This is also in a picture from album of fluid motion of Milton Van Dyke, one of the best albums. You can find it for free, and it has hundreds of pictures of very nice quality. Just to understand, it's important to understand the flow pattern in real cases. It gives a clear understanding about some concept we would like to calculate or simulate numerically. Nowadays it becomes more and more important because this album is something that you can obtain once you use numerical software like ANSYS Fluent, for example. You can obtain same or very similar picture in CFD software and validate by flow structure, at least by quality of flow, to have this qualitative comparison. You can see flow structure is not symmetric on the front and the rear side of sphere, so it means that real sphere always has drag, right? Even though if calculated by potential equation, sphere did not have any drag. So flow is not symmetric, drag exists. Let me see other case. This is a high Reynolds number. First one was Reynolds 15,000. Next Reynolds number is 30,000. You can see different turbulent structure on the rear part of sphere. Front part of sphere is almost same. Flow is smooth, but behind sphere we have a more higher turbulence level mixture. We cannot determine any more vortexes as we saw on previous picture. We see only a smoke which is composed by almost chaotic movement of infinitely small vortex structures, and the large vortices and the small vortices combined together produce this complex flow structure. Next slide shows to us drag coefficient for sphere for different Reynolds number. First part of this figure shows laminar flow. It's mostly, I think, until this value, until some thousand of Reynolds number. And then at high Reynolds number, drag coefficient becomes constant, more or less constant, and this is a characteristic of turbulent flow. At turbulent flow, drag coefficient stays approximately constant. Then at extremely high Reynolds number, we have this behavior, typical behavior for sphere or for cylinder. You can observe it also for a flat plate. You can find very similar change or jump of drag coefficient. I think it's related with the change of flow type, compressible, supersonic. Okay, please let me know if you have some questions on previous discussion, and you can write in the chat. Meanwhile, I can tell you about airplane lift and drag, an approach, simple approach that can be used related to three-dimensional body. And the simplest approach is to transform airplane to just a wing without fuselage. Okay, or let's say to use an equivalent wing that creates a same lift as would be created by complete airplane. So we do not see a fuselage, and we see only the wing as the main source of lift. Of course, we understand that nowadays well-designed fuselage also can produce significant value of lift. But for approximate calculation, for preliminary calculation, such structure can be excluded. We understand that in such case, error can be significant. We speak about 20–25% of error, at least. The airplane drag can be calculated with that approach, and here we have drag coefficient offered by references, is reference 2 from Anderson book, and you can see the values of lift coefficient, drag coefficient for different angles of attack. A typical value is not for all possible airplanes. Is the typical value that lift coefficient can be a bit higher than 1, 1.3, 1.5. Drag coefficient for different angles of attack starting from 300s to 1600s, 1500s more or less. And because of this, lift to drag ratio can be approximately near 10, 12. Anderson also gives to us ratio or relation between lift and drag coefficient as a function of aspect ratio of the wing. This equation you can see here, equation 21 and 25 are correlated because E coefficient is defined as a function of aspect ratio, and equation 25 is purely empirical. So it's obtained by experimental analysis of different airplanes. With equation 21, we can obtain drag, so we can obtain required thrust of engine for known geometry of airplane with known aspect ratio, and also lift to drag ratio, which you can see on the right side of my screen, which can give us the lift coefficient and which can say how much could be the weight of this airplane, of this structure, as a function of aspect ratio and as a function of zero drag coefficient for, I think, for the airfoil, if I'm not wrong. Yeah, CD0, supposed to be some drag coefficient. So that's it. As I told you, part 6 is extremely short, very small. We close it at less than 40 minutes. I would like to see if you have questions. I would like to thank you for having lectures of aerodynamics with me. And now we can work more closer with your questions, with your practical tasks. And our next classes, as I already announced, would be work with problems that you ask, or questions which you ask to me, and I recommend you every time some videos to see from previously asked questions. I think it's important to understand that many things that you probably would like to know already was explained by me, and it was asked by other students. So we will not follow the same way of answering these same questions which already were answered. Please let me know if you have questions.
Professor, I do have one question, but it's actually related to simulation and not the theory part. Would you like me to wait for the end of the class?
No, we can talk today since we have time.
Okay, so I was working on my simulation for work 2, but I stepped into a problem that I really never happened to me, so I have no idea what I did wrong. So I was thinking if you could instruct me on this. The problem is the following. I did a simulation on the airfoil, I'm working on, and I prepared the control volume. I did all the steps, created the mesh, and when I did the simulation in Visid, simulation would not converge. But at first I thought it was a problem on the mesh, so I started working on the mesh, refining it, and seeing if everything was coherent, if all elements were similar with the other next to it. But the problem persisted. But the strange part is that when the problem persisted, I suspected it wasn't the mesh. So I tried testing in another simulation method. I tested it in, let me just check it for a second. I tested it in standard K omega model just to see if a different result would come. And when I tested it in this model, the simulation converged perfectly. So this actually never happened to me. So I think it's in other simulations that I have done, it's more common to converge in Inviscid and not in standard K omega, and not the opposite. So what maybe did I do wrong? If you want to, I could show the mesh, I could show the parameters.
Oh, nice question. Thank you. Is typical this problem when Inviscid flow does not converge, especially when you choose high order of approximation. Probably you chose second order of approximation for Inviscid flow. Is it true?
Yeah, that's correct.
So now we understand. The problem is that is called computational instability. That I've tried to explain probably last time. Do you remember when we overestimate or underestimate process or some values in between points, and it becomes not physical, understands that this problem exists, tries to apply corrections, then receive different results on the next step, and then on the next step also analyze that the problem persists. So it's if we read in the book, it will be called dispersion of approximation scheme. I think would be nice if we see the simulation, but probably better would be to do really on next class. Let's move it on next class on Thursday. We could see it and we can discuss. If you share the simulation with me before, just to take a look what is happening inside simulation. But I already suspect that with the second order approximation method, you approximate in some zone, or not you, sorry, program approximates in a wrong way that tries to provide correction in each step that results in oscillation of some flow properties. This is our dispersion. Okay, that's the problem. So try to change to first order of approximation. And when you use viscous model has dissipation term inside. Viscosity is dissipation. So it dissipates problem inside the computational volume, and this problem disappears and flow converges just because viscosity is present. So all these small oscillations which non-viscous part is making are diffused by viscous model. So this is why they do not appear inside viscous simulation. Understood?
I see, perfect. I will change the model then.
If you want, and if you downloaded the book, which I recommend you, of Fletcher Anderson Tannehill, I can give you the page number which describes these two processes, and you will be more familiar with this before we start talking on Thursday. And if you still will need to do it, because my recommendation is reduce to first order of approximation, and probably problem disappears.
Okay, that's perfect. Okay, thank you, Professor.
Thank you very much. Other questions? Okay, I see no more questions. We do the following. I expect your questions in WhatsApp. You let me know, because it's the primary messenger I'm using. And when I receive that you have something to discuss, it can be a personal message, can be message inside group, then we arrange time, probably during class time, and we discuss and see your problems. I would like to help you with your simulation, something that you cannot solve by yourself, something where a monitor cannot help. since we have time, I can help you with this, and I think your quality will improve significantly when you obtain such support. So people, thank you very much for today. We finish. For next classes, we meet according to your questions. If will be no questions, I recommend you videos to watch with my previous classes, where I answer a lot of important questions about simulation and theory. Okay. Have a nice week and see you next time. Thank you for participation today.
Thank you very much, Professor. Till next time.
See you.